Okay, so now we actually want the line of best fit that is perfect. The one we did here seemed to fit okay, but maybe someone else would have thought this was a little better, or that was a little better. So we want the one that's the very, very best. Okay, so that is the least squares regression line. And here is our data again. Notice they finally changed it to centimeters. Okay, and so we want the one that fits it perfectly. And the one thing we know is it'll go by through X bar, Y bar, and we either need a formula, or a calculator. Let's talk about how we're going to do it first. We're going to do this thing called minimizing the residuals. A residual is the vertical distance between a data point and the possible line of best fit. So if this is our possible line of best fit, this is the actual point. Maybe this was somebody's height. Okay, 160 and 29. I don't know, I'm making stuff up. But this is what our line would have said it is when we go through all the points. It's our line of best fit. So a residual is this difference here. Okay. And if this number is, if the actual point is above the line of best fit, the residual is positive. If the actual point is below the line of best fit, the residual is negative. Okay, so how do we do it? Let's just start by looking at some data points. You have this picture, and I've gone ahead and given values to it. So I scaled it, pause it, and write it in if you have to. And I will tell you that the actual data points are the point, you can see it pointing right here. This would be the point 2, 4 over 2 up 4. This other actual data point is the point, and I have to look at my notes very carefully. Let's see, well, it's over 4 and up 2.5. Okay, over 4 up 2.5. Yep, that's right. And then my last data point, actual data point, is over 5 and up 5. Okay, and so then what we did is we have the line of best fit going through it, and we have the points that are on the line. Well, they're going to be the same x, right? It's still over 2, but it's up a different amount. In this case, it's over 2, and it's up 2.5. In this case, of course, it's still over 4. It's written over here, but we're talking about this point over at 4. And it is up, it looks like 3. Yep. Okay. And then this one right here, it's also over 5. And it's up 3.5. Let's see, yeah. 3.5. Okay. So we have our actual points and our prediction points. Now, what we want to do is minimize these residuals, otherwise known as these distances. Well, just like with standard deviation, we need to measure the distance from here to here. So we do that. We take the actual data point. We'll make this first one orange. And our actual point was at, we know the x's are both 2, so we don't care. Our actual point was at 4. The prediction point was at 2.5. And then just like standard deviation, if we just wrote that down, that's a positive difference of 1.5, but we have to worry about positives and negatives, so we square it. Okay. This next one, I will do it as purple, so we're talking about this residual right here. Okay, the actual data point was 2.5. The y on the line was 3. So that's a negative 1.5. You guys see how if I just added them without squaring them, they'd cancel each other out, just like standard deviation. And the last one will go brown. Okay. And so my actual data point is up at 5, with the prediction being at 3.5. Okay. And we would get 1.5 again, and we'd square it. And these all little ones had squares, part of the formula. So just put them in. Okay. And if you were to take these squared values and add them all up, you'll have 4.75. 5. And this is the sum of the squared residuals, okay, otherwise known as S. And what we want to do is minimize S. We want it to be as small as possible. When it's the very, very smallest, then we know our line fits the best. So again, we need to minimize S for every residual in the group. And I will show you a demo of that in class that makes a lot of sense. So until then, let's just go with the formula that'll do this for us. Okay. So you can probably imagine the time-consuming work needed to find M and C, or we're used to M and B, which would be slope and y-intercept, especially with 20 or so points, not just 3 as in the situation above. So we have a formula. Now if you notice this formula, it looks like the one I did before, y minus y1 equals m times x minus x1 on the end of the last video. And it's exactly the same thing, except for the one point we know our equation has to go through is the average of the x's and the average of the y's. And then to find our slope, it's given by the standard deviation of the x and y's multiplied together plus the standard deviation of all x values squared. And we'll talk about that in just a minute. But we're going to use some points and fill in this formula. So we have the points 1, 3, 3, 5, and 5, 6. So this will be on your homework. You'll make a table like this and you'll put in your x and y points. So we have 1, 3, 3, 5, and 5, 6. And then we're going to go ahead and add them up. Okay. So 1 plus 3 is 4, plus 5 is 9. We have 8 plus 6 is 14. Okay, so and then you can go over here. That means the sum of all the x values was 9. The sum of all the y values was 14. You will need all of this on your homework. I can't say it again. And then x times y. So 1 times 3, I'm going to make this a different color, is 3. 3 times 5 is 15. 5 times 6 is 30. And if you add those up, you'd get 48. So the sum of x times y. Okay, and then x squared. Well, let's see. 1 squared is 1. 3 squared is 9. 5 squared is 25. And I promise you, if you add those up, you will get 35. So we need all of these pieces for our formula. And then again, n is just how many numbers do we have? 1, 2, 3. Or how many data points do we have? 1, 2, 3. So n is 3. Now let's look at our formula. We need an average of the x's and an average of the y's. Well, remember, when you take an average, it's adding up all of the numbers and dividing by the total number of numbers, right? So we have 9 divided by 3, or 3. Our average x is 3. And if you did the same thing for the y's, we'd get 14 divided by 3, and that doesn't simplify into anything nice, so you could make a decimal or just leave it like that. And I'm just going to go ahead and leave it like that for today. Now we need S of xy, which is basically the standard deviation of multiplying x and y together. Don't worry about it, other than here is the formula for it right here, and it's part of our formula up here. So we need the sum of the x's and y's. Okay, so the sum of my x's and my y's were 48, and I need to divide that by the number of points, which is 3, minus x bar, y bar. Well, let's look. We've already figured it out. Our x bar, or average x, was 3, and our average y was 14 thirds, which is nice because these now cancel out. And I promise you, if you simplify all of that in your calculator, you will get 2. Be very careful, try that on your calculator. Now we need the second part of this equation, okay? The standard deviation of x squared, which is the sum of the x squared divided by n minus the average x squared. So again, the sum of my x squareds, and I'm going to pick a different color this time. Excuse me. Okay, so that's 35 over 3. And our average x again was 3 squared. And if you simplify that in your calculator, you'll get 8/3. Okay. So I actually want to show you how to do all of this in the calculator. Okay, and I guess not all of it, because I could show you how to put this part in the calculator, the columns, but more so I want to make sure you put this part in the calculator correct. So, okay, for the standard deviation of x times y, parenthesis, 48 divided by 3, and again you can do it by hand, but check yourself, minus 3 times 14 divided by 3. And I am just putting this in, and you get 2. Okay, let's try the next one. 35, you can never have too many parentheses. You can under parentheses, okay, and I probably didn't need one there, but that's okay, minus 3 squared, and I get a decimal, but I wanted it as 8/3, so you go math, frac, and there's our 8/3. So you can do it by hand or in the calculator, okay, with any of this. Let me move this out of the way. Full screen. Okay. So lastly now though, we're going to use our formula, and our formula is just plugging in everything that we've just gotten. So our formula says we have y minus x bar, or excuse me, y bar. Y bar is 14/3 equals the standard deviation of xy, which is 2, all over the standard deviation of x squared, which is 8/3, times x minus the average x, which is 3. Okay. Now at this point, you can put them in the calculator if you want, and you will get y minus 4.67, which is approximately equal to 0.75x minus 2.25. You could also keep them as fractions and not need the approximate. Add 4.67 to both sides, and you get y is approximately equal to 0.75x plus 2.42. And this is our perfect line of best fit. Hallelujah, this is the line that's going to go through at best. So let's see, 2.42. You can go up here. Well, we're going to run out of time, but if we graphed it, it would be the best one, and I'll show you that in class. The last thing you have to watch for is interpolation, and extrapolation. Basically, we're going to use these lines to help predict stuff, but if you go too far out of your data points, you might have an error, or too far below your data points, you might have an error, and we will discuss that a little bit in class as well. I just wanted to use this as a prediction. So this is a y hat equation because it's a prediction. What if I wanted to predict, and no wonder this wasn't going to fit our original data. What if I wanted to predict the value of y when x is 2? Because we don't know that. We know it when it's 1 or 3. I'd plug it in and I'd say I want to know the value of y when x is 2. And I would quickly plug that in my calculator. 0.75 times 2 plus 2.42, and it would say it's going to be about 3.74. And if we go back up and look at our data, that makes sense. It'd be 2 and 3.74. So that's how we use this. Please be prepared to have this filled out in class next time and come with questions. Also, don't forget your pumpkins if you're buying a pumpkin.